Welcome. In this video, we're going to discuss the net change theorem. But before I talk about that, let's recall this is something we've already been doing a lot of. We started with some integrals of, say, a velocity function, v of t, in, say, miles per hour. This is something we've already been doing. And we've figured out that what we end up with here is actually just miles. Really, what you end up is with a position function. All right, so now that we have that out there, let's actually go into the net change theorem. So the net change theorem tells us that the integral of a rate of change is the net change. So if I have the integral from a to b of f prime of x dx, and that's a big F, I end up with big F of b minus f of a. So this is the net change of the antiderivative. All right, so let's say v of t is the volume of water in a reservoir at time t. Then the derivative of this function is the rate at which the water flows into the reservoir at time t. And so the derivative of this function is v prime of t. And if you notice, that's what we have here below. We have the integral of v prime of t. So that's the integral of a rate of change. So the rate at which the water flows into a reservoir at time t. And this is from time 1 to time 2. So what this is telling us is the total amount of water that has poured into the reservoir. So this is the total amount of water that has flowed into the reservoir between times t1 and t2. So let's keep going. If the rate of growth of a population is given by dp over dt, then the integral here from t1 to t2 of dp over dt, and I express it here, it's equal to p of t2 minus p of t1. Well, that's actually representing the change in population between time 1 and time 2. So that is the net change in population. All right, finally, if s of t is the position of an object at time t, then the derivative of this function, s prime of t, is the velocity. That is the rate at which the position changes over time. And this integral from time 1 to time 2 of the velocity is going to give us the position change. So the overall takeaway is that any time you integrate a rate of change, you end up with a net change. So again, if this rate of change that water flows into the reservoir, if we integrate that, we end up with the net change in water in the reservoir. If we integrate the rate of change of population growth, we end up with the net change of population growth. If we integrate the net change in position, excuse me, I said that wrong. If we integrate the rate of change of a position, then we end up with the net change in position. Let's explore this net change a little further. So recall that a of t is the acceleration of an object at time t. So if we have a position function s of t, then s prime of t is equal to the velocity, and the second derivative of t, which is the first derivative of v, is equal to the acceleration. So we want to express the change in velocity between t1 and t2 using the net change theorem. So the change in velocity, so that's how much the velocity changes between these two times. This is the net change in velocity. If we're using the net change theorem, then we need to rewrite this as an integral. And so what is the antiderivative of velocity? Well, that would be acceleration. Acceleration measures the change in velocity. And this would be between t1 and t2. I hope this video was helpful.